And so the next talk will be given by Simone Dellagnello, talking about MoonLIGHT. And Simone, you have 15 minutes. I will let you know when you have 5 minutes remaining.
Thank you, Slava. Can you hear me?
Yes, perfect.
Okay, so this is a talk about lunar laser engine and laser reflectors. So this introduction, the wide introduction given by you, Slava, was very useful to set the stage. I'm going to be talking about MoonLIGHT, which is a next generation lunar laser reflector for gravity and geophysics, and it's point and actuator MPAc. So I'm giving this talk on behalf of a collaboration of people from INFN Italy, University of Maryland, Doug Curry, the Italian Space Agency Space Geology Center, University of California, San Diego, Tom Murphy, and at the Center for Astrophysics, John Chandler, and two universities and INFN units in Italy, in Padua and Naples. Next slide, please. So the outline is the following. I'd like to introduce the international framework of our effort with the recent selections and missions, describe in general MoonLIGHT and MPAc, and then discuss the scientific objectives to conclude with the further discussion on the international framework and specifically the science studies which are going on right now and the future opportunities. Next slide, please. So this is the international framework. Our core instrument, the next generation lunar laser reflector, has been developed together with the University of Maryland by Doug Curry and our group in Italy, near Rome in Frascati. We have proposed this instrument together to ESA and to NASA for lunar missions. We were selected both by ESA and NASA. So recently in 2019, our MoonLIGHT reflector, which is the same core payload that developed with University of Maryland, the pointing actuator, a dust cover actuator, has been selected after a lunar science request for information. We are now under contract. And we have a launch agreed between NASA and ESA. It will be Eclipse mission with participation by ESA under PRISM 1A. And it will go to the Rainer Gamma crater at the end of 2023. Our science PI is Marco Muccino from INFN. Similarly, in the US, Doug Curry presented the proposal. We are a co-PI group with him. He was selected in 2019 by NASA within the Lunar Science Instrument and Technology payloads. The launch is foreseen at the end of 2023. It's a NASA Eclipse mission. The mission is called Blue Ghost, and it will go to the Mare Crisium. Next slide, please. So our mission, PRISM 1A Eclipse, so in jargon is CP11, will go to the Rainer Gamma crater. As everybody knows, it's a swirl. It is associated with the magnetic anomaly. Its coordinates are close to 59 degrees west, so it's pretty close to the lunar limb in that region, so it's very useful for lunar laser engine measurements. Next slide, please. So this slide is just to catch your attention again on the core functioning principle of cube corner reflectors and lunar laser engine. They are typically mounted with the mounting rings inside a metal frame. The comics at the bottom of the page just shows you that the time of flight from any laser on the ground and back is close to 2.5 seconds. Next slide. So we are working in Italy with the Italian Space Agency. We have a joint lab completely dedicated to laser reflectors and laser engine. We're also partnering with NASA Survey, which is managed centrally at NASA Ames in Silicon Valley. We have an affiliation partnership since 2014 and an association at Space Agency level since 2017. So in this picture, you see the kind of payloads and destinations on which we are working with a number of partners, ASI, ESA, NASA, Survey. We made reflectors which are now on Mars with the recent Mars surface missions. We are working on Earth observation payloads. I will describe the main laser reflector for the moon in this talk. Then at the bottom, you see large reflector arrays, which we are manufacturing now for Thales Alenia Space and Airbus for Galileo second generation. At the bottom left, you see a model of the Legios spherical satellite, which is used for geodesy and to measure the land steering effect. Lares 2 has been manufactured by us, INFN, and delivered to us at the end of 2020, and that will be launched by ESA in early 2021. So it's another experiment which is useful for test general relativity, in particular the lens steering effect. And then we are also making smaller microreflectors for comet and asteroid missions, like the ESA Hera mission to the Didymos double asteroid. Next slide. So we have a facility which is completely dedicated to laser reflectors and ranging. We have 2 optical ground support equipment facilities, which are equipped with optical benches capable of measuring the diffraction response and the piezointerferometry of single reflectors. We use this to establish the correct performance in space and a TRL of greater or equal to 7. We have 2 of them, one dedicated to GNSS and the other one for the remaining missions. We have 2 M0 solar simulators, which are faithful up to almost 1,000 nanometers, and we perform infrared thermometry, non-invasive, in order to measure the behavior of reflectors in space. Next. So quickly, why did we go from arrays to single reflectors? Basically, the laser return by single large reflectors is roughly comparable to the one of the Apollo arrays. This is because the laser return scales as the 4th diameter of the power. Initially, then, our reflectors will clean from dust. Therefore, we will not suffer from the factor of 10 reduction, which has been estimated by Tom Murphy et al. In the paper you see at the bottom. So we expect that in the beginning, for the first years, 5 to 10 years, the new reflectors will perform as well as the Apollo reflectors. Next. So the next slide shows that if you have a single reflector instead of an array with a size of about 1 meter, like the Apollo reflectors, then you are unaffected by the broadening of the time broadening of the return pulse, laser pulse from the moon. And so with the sparse arrays of single large reflectors, you have basically what you see at the plot at the bottom right, which is a wide pulse of 2 nanoseconds becomes much, much narrower, potentially very, very narrow, just limited by the width of your electronics and detector response. So the new reflectors developed by Maryland and INFN will give a range accuracy which would be below millimillimeter for a single shot from an instrumental point of view. So talking only about the space segment. Next slide. Our reflector is embedded in a device called MPAc, MoonLIGHT Pointing Actuator. It consists of an azimuthal frame which is interfaced to the lander. We have an aluminum frame which holds the housing. And then we have motors and actuators in order to point the axis of the reflector towards the center of the librations as seen from the moon. So towards the center of the Earth, as seen from the moon. We also have an actuated dust cover, which is supposed to protect the reflector front face from the regolith dust during and right after landing. We are supposed to open the cover after 72 hours from landing, and then do the pointing afterwards. Next, please. This table, I will not go into the detail, but it summarizes some of the important features of the payload of the MPAc pointing actuator. It's a work in progress. Basically, we have a total mass, including the reflector, so all inclusive of 4 kilograms. The size is about 25 centimeters in all 3 directions, and NASA is allowing us a 25% increase of that volume. And then we have a SupraSeal reflector, SupraSeal 311 reflector, which is very good grade of fused silica. And then all the accessory pieces in terms of plastic rings, KLF, the aluminum, the back housing, etc. We are going to use less or equal to 10 watts of power per pointing attempt every 1 hour time slot. And then we're going to coat the payload with an appropriate painting, the HZ93 white inorganic coating, in order to save the thermal balance of the instrument. Next slide. We also have an actuated dust cover, which does the function I just said. And you see here one of the 2 or 3 designs we are considering. So you see the cover closed on the front face of the reflector, the cover open, and then you see on the right 2 other views of the cover open and close from a side view. So this is an important part of the whole payload. MoonLIGHT plus MPAc plus activated dust cover. Next slide. The scientific objectives we want to achieve. So Slava did a very comprehensive introduction, so I don't need to go into any detail of this, but just remind you some of the topics we want to work on. The equivalence principle, so it comes into flavors, the weak and strong equivalence principle. We want certainly to contribute to the measurements of the possible time violations of the fundamental constants like the Newtonian big G.
5 minutes left.
Yes, we want to test metric theories by measuring the post-Newtonian parameters and then study fundamental properties of the moon interior. So this is something we want to do with the Lunar Geophysical Network, which is a global effort started more than 15 years ago, now led by Clive Neal and René Weber. Recently, we published a paper, Haviland et al., which you can find at the bottom of the page, which explains how we chose the landing sites for this proposal. Next, to do the analysis, the physics analysis, we use the Parameter Refinements program by the Center for Astrophysics. It takes as input a solar system model. It does numerical integrations using observations and then parameter estimation. It minimizes the observations minus the computations in terms of residuals. And then it gives results in terms of physics parameters, which you can find at the following slide, slide 15. This is something which has been discussed already by Slava, so we'll not go into further detail. Just to tell you that the second column shows the current status. The next column, the third, shows what we can do with 1 millimeter accuracy. Then the time scale, and then the last column shows what is the ultimate goal of this effort on reflectors, ranging, and physics analysis. And that requires a network of reflectors on the moon, which I'm going to discuss in the following slide. So slides 16 and 17 show a different analysis, which is not a test of general relativity, but it's a test of an extension of general relativity in terms of space-time torsion. So general relativity includes the curvature of space-time. A more general model of space-time can include torsion. So we studied this by using a model of space-time torsion published by Guth, Tegmark, and Kabi. And we put constraints on the parameters of the theory by looking at the orbits of the moon and Mercury. So for the moon, we use the geodetic precession, the lunar laser ranging data. For Mercury, we use the radar ranging data. And if you go to the next slide, 17, you will see that we also did this analysis with LEGIOS, the spherical satellites. So it is possible to test new theories of gravity with lunar laser ranging beyond general relativity. Now, the last two slides are, again, international framework. I want to point out the science studies which are going on right now. So lunar laser ranging science is part of the ESA Fundamental Physics Roadmap, which is being issued by ESA right now. If you look at that link at the section 5.1, you see the solar system test with the lunar laser ranging measurement listed. There is a topical team study on lunar geophysics led by Mark Biekzorek. This is actually a team which includes many US representatives like Neil and others. So we will study how to make a geophysical package synergetic with the Lunar Geophysical Network to improve and increase the number of measurement points on the moon. In the long term, ESA has a new lunar program, a vigorous lunar program, and it foresees a European large logistics lander, which will be able to deliver many hundreds of kilograms of payloads to the lunar surface. So that's a good prospect for the next 10 plus years. And then we performed in 2020 a Lunar Geophysical Network mission concept study funded by NASA. Lunar laser ranging is one of the core technologies, like for the Apollo reflectors. The final report, you find it at the red link at the bottom of the page. It describes the whole project and the opportunity of proposing this for the New Frontiers announcement opportunity, which is about to be issued by NASA. Last slide, conclusions. So this summarizes what I discussed and some of the things that Slava introduced before. So in the next few years, the reflectors will be back to the moon after more than 50 years. Our device will be capable of doing a robotic pointing to Earth, to the center of the Earth librations as seen by the moon within 3 degrees. It will provide a laser return comparable to Apollo arrays. This is the payload that we have developed together with the University of Maryland, being proposed to ESA by us, INFN in Europe, and by Doug Curry, University of Maryland, to NASA in the US. It does overcome the calibration issues, so the current laser range error budget, which is limited to 2 centimeters, can be improved down to 1 millimeter and less. So we will be able to work on the equivalence principle, study possible variations in the Newtonian big G constant, test metric theories of fundamental gravity through estimates of the ppm parameters, like we did already in the 2 papers I showed for space-time torsion. This will be a great tool to monitor the lunar interior.
Time is up.
Yes, so I want to just say that the ultimate science goal can be achieved with multi-missions, so the ESA-L3 program and a full-blown LGN that hopefully will be proposed and approved by NASA for the New Frontiers 5. That's all.
Excellent. Thank you very much, Simona.